I keep letting my plants die from neglect. I'd love to stop doing that. In fact, what I'd love is to have a wire-free, smart plant care device that could remind me when I'm neglecting my houseplants into an early compost heap. But as it turns out, in trying to solve this problem, I ultimately discovered a much more important problem that I'd have to solve first: batteries in the smart home. And there's no point swapping forgetting to water my plants with forgetting to charge the smart device, so it's going to have a long battery life. So to realize my dream of creating a basil plant that can literally demand my attention, I set out to create a compact, modular, energy-dense battery pack that supports all the I2C sensors in my smart home and can provide several years of use without ever needing a charger. As it turns out, this was considerably harder than expected, but I managed to create something that I'm pretty proud of. If that sounds interesting to you, let me show you how I did it. Originally, when I set out to solve this problem, I kinda thought it would be pretty straightforward. Take a microcontroller, a decent soil moisture sensor, and a battery and slap them together. Boom, problem solved. I could not have been more wrong. Here's what I was going to do. You can get cheap resistive soil sensors that apply a voltage and measure the resistance across two probes stuck in the soil, but the exposed metal degrades, making them unreliable over time. Instead, you can get sensors that also have two big pads of copper, but they're hidden under the solder mask. They're not in direct contact with the soil. Instead, they act like a capacitor, and they measure the soil moisture through capacitance. I got this one from Adafruit. For low power applications, the NRF52840 from Nordic Semiconductors is one of the most energy efficient chips available, and Seed makes these tiny, feature-rich boards that have them inside, so this seemed like a no-brainer. And then there was the battery problem. Where I live, lithium batteries, especially reliable ones, are hard to find. I did consider skipping lithium batteries altogether. They're kind of a pain to deal with anyway, but if we look at the numbers, AA and AAA just can't compete. Alkaline batteries, the non-rechargeable ones you get practically everywhere, have a nominal voltage of 1.5 volts. For rechargeables, it's even worse at 1.2 volts. That's a problem because our sensors and microcontroller can't work with voltages that low. We'd need at least 3 cells in series to get above 3 volts, or we'd need to use a boost converter which would have losses and consume even more current. With lithium, the nominal voltage is 3.7 volts, so we're set with just a single cell. And even if that wasn't a problem, there's the energy density. Actual battery capacity depends on a bunch of factors like temperature and the amount of current being drawn, but roughly speaking, an off-the-shelf AA only has half the energy of a small lithium cell, and I expect in reality it would be a lot less, or it might not even work, because there are times where the microcontroller suddenly needs high current to power its antennas, and I was concerned the alkalines just wouldn't be able to meet that demand. So I went with lithium-ion. Researching online, Encon.nl seems to be widely recommended in Europe, and they mostly stock these cylindrical cells. If you've done any battery projects yourself, you've likely heard of 18650s. They're kind of like an oversized AA. But lithium cells come in a bunch of other sizes, including the smaller 18350. These cells are small but dense, and they come in capacities around 900 to 1600 milliamp hours. Lastly, I'd like this device to be versatile, so I'd like a way to optionally add or remove sensors like light or temperature sensing. So I ordered a bunch of parts, batteries, and some sensors, and got to work designing a way to link them all together. Now, I wanted this device to be secure, long-lasting, and modular, so no sticking everything together with hot glue. I need a way to attach the MCU, the battery pack, and any sensors in a way that's mechanically sound and that can be taken apart without tools. I thought about 3D printing a kind of spine and having the devices clip on or slot into place, but PLA suffers in sunlight, by which I mean it has a tendency to melt. Given that this first and foremost is meant to save my plants, and said plants thrive on sunlight, this just wouldn't be viable. PLA also suffers from creep under constant force, so the clips on the battery holder might come loose over time. That's not great for long-term reliability. Now, there might be other 3D printable materials available that don't suffer from these issues, but I don't even own a 3D printer anyway, so anything more advanced than this just didn't seem like a good lead for me right now. Instead, the battery holder clips are designed to attach to PCB, so I could just use a basic PCB with holes for the battery and maybe add some headers to fix the MCU in place. And then for the battery management, the Xiao has these battery pads, which would solve the problem of how to connect a battery. They're a little awkward to access from a PCB, but you can get these sprung pogo pins that would stick up from the board and compress to keep contact with the underside of the Xiao. I have no experience with PCB design, so I really wanted to avoid overcomplicating the design because I knew it would just become an absolute time sink learning how to do anything properly. So, with my plan all perfectly laid out and ready to go, I immediately got to work solving all of the problems I had just created for myself. straight off the bat, I realized 3 major flaws. The Xiao does indeed have a pair of battery pads, and you can even use them to safely charge a battery over USB up to the lithium cutoff voltage of 4.2 volts, at which point it halts charging so your battery doesn't explode. Sweet! However, the internal circuit these pads connect to does not provide over-discharge protection. Meaning, if you attach a battery to these pads and you actually want to use it, there's nothing to stop the battery discharging to a dangerously low voltage and risking ruining the cell or possibly even causing a chemical fire when you try charge it again. Luckily, you can get batteries that have a protection circuit built into the cells. So great, problem solved. I ordered a few protected cells from Encon and pressed on. Unfortunately, around then, I came to a second realization. I figured if the microcontroller was in deep sleep, the sensors couldn't draw power. But it turns out that's not the case. To make things worse, the soil moisture sensor I wanted to use is actually a little smarter than most sensors. This thing has an entire AT-tiny microcontroller on board to convert capacitive readings into user-friendly moisture level readings. For lots of reasons, I'm sure this design is very clever, but for my battery life, it's killer. It draws like 5 to 10 milliamps continuously, which would tank our battery life down to just days. You could design your own soil moisture sensor without the AT-tiny, and I considered it, but I figured it's just way above my current skill set and it would take a long time to understand how to do it right. With this issue ringing in the back of my head, my new cells arrived, and I realized yet another problem. 18350 batteries are called such because they're about 18 millimeters in diameter and 35 millimeters in length. So when I bought a nylon 18350 battery holder, I assumed any 18350 would simply slot into place. I have here that holder and the protected battery pack, and as you can see, we have a problem. Turns out the protection I see is placed on top of the positive terminal, and it adds a few millimeters to the size. That sounds small, but it's about 7% of the overall length, enough that protected cells simply won't fit in these mass-produced holders. So just get a holder that's designed for protected cells, right? Well, I couldn't, and after searching around online, it seemed like I wasn't the only one. I think this is because most manufacturers making these cells are doing so for mass production, not for hobbyists like me, and the pros probably prefer to make their own protection circuits and just use these unprotected cells. So now, my plan had some serious problems. If I wanted to use the Xiao's battery pads to supply the microcontroller with power, I'd have to use protected cells. But if I used protected cells, I'd need to find a battery holder they'd fit in, which I couldn't seem to do. Now, unprotected cells do fit in the holder, but if I connect those to the pads, I'll ruin the cell when it over-discharges and probably kill my plants in a house fire. So, after a lot of thoughtful contemplation, I eventually accepted my fate. If I was actually going to pull this off, I'd have to learn PCB design and create a custom PCB that would both manage the battery and cut power to my sensors in deep sleep. And in a characteristic stroke of good luck, a company reached out to me right around this stage in the project and offered to sponsor the build. What do they provide? Custom PCB manufacturing. I'm not even kidding. Sometimes you just get lucky. So massive thank you to jlcpcb for sponsoring this build. jlcpcb provide easy, affordable and reliable PCB and PCBA manufacturing. I don't have an SMD soldering setup at home, so PCBA opens up a whole world of custom engineering builds that I just couldn't achieve without a company like jlcpcb. PCBA means I can focus on the design and the prototypes arrive ready to go immediately. Upload your Gerber file, get an immediate quote, and order in minutes. Their online tools make ordering as easy as online shopping. I had no experience with ordering custom PCBs before making this video, and I found the whole experience intuitive and frictionless, with every option clearly explained as you make your choices. You can have your boards produced in as little as 24 hours, and the boards can be got for as little as $2 with 1 to 8 layers. Once ordered, you can track your boards in detail as they move through this fascinating manufacturing process, including a host of electrical and quality checks. So don't miss jlcpcb's 6-layer PCB special. Find out more with the link in the description and enjoy $123 in coupons for new users upon registration. After weeks of learning KiCad and iterating the design in software, this is what I ended up with. I was hoping that there would be some magical all-in-one battery management chip that I could just drop in and it would do everything, but that didn't turn out to be the case. Instead, I went with a 3-chip design. Lithium battery voltage changes depending on how charged it is, and not all MCUs and sensors can handle that. So the first chip here takes that variable voltage and gives me a stable 3.3 volts. Then the second chip provides the battery with all those protections we need. Overcharge, over discharge, short circuit protection, this baby's got it all. It's connected to a pair of MOSFETs, so if this IC thinks anything dodgy is going on, it'll open the circuit using those MOSFETs, disconnecting the battery. Lastly, plugging a USB cable into the microcontroller provides it with 5 volts, so this third chip takes that 5 volt line and uses it to charge the battery. It also allows the system to continue operating even while charging. Then, to solve the power-hungry sensor problem, I placed a MOSFET on the trace that provides power to all sensors. The gate for this MOSFET is connected to one of the microcontroller pins, so we can switch it on and off in software, powering sensors only when we actually need readings. Extra sensors can be attached using the headers above and below the Xiao, either directly like this, or using standard jumper cables if you need to cover some distance. Lastly, I added a temperature and humidity sensor directly onto the board because they're cheap and pretty much any use case I would have for one of these boards benefits from having one. I also just cannot get over how tiny these components are. Here's the tip of my finger for scale. As soon as I got the boards, I got to testing my circuit. I was wary of just chucking in an unprotected lithium cell into an untested board. If you've ever seen a lithium fire, you'll know why. I wanted to make sure the protections were working in case my board had some fatal flaw. I checked the board for shorts, then tried with a USB cable, then faked a battery with a power supply, and finally I tested with the battery itself. And at first, the results were really promising. No shorts, then the board powered up with just a USB cable, and I could even flash it with ESP Home and have it reach Home Assistant. Then I tried to take sensor readings, and things just immediately broke. The onboard temperature sensor worked just fine, but when trying to use other sensors like this light sensor, the board would just error out and fail to see it at all. No matter what I did, I just couldn't get the thing to work. After a lot of testing, I had a sneaking suspicion of what had gone wrong. Essentially, what it all boils down to is inexperience and stupidity, but more specifically, the problem I'm facing is a missing pull-up resistor. So I made a breadboard circuit to test my theory, and immediately the sensor reading stabilized. It's great to know what the problem is, but less great when you know that you can't fix it. This problem had gone on way too long already, and I couldn't afford to wait for a new revision to arrive, so instead I tried a workaround. I learned there are pull-up resistors on the Xiao that you can access in software. This makes the code a little messier, but it should save the prototype. The real fix is, of course, to add the forgotten resistor, so I'll be adding this to the design by the time this video is released. With the sensor stabilized, I moved on to simulating the battery with a power supply. Just a small aside here, this protection IC triggers a shipping mode that cuts the power when there's no battery connected. So to get current flowing, you either have to connect the USB charger or short battery plus to ground. I have no idea how things would shake out if I tried to connect the PSU and the USB cable, and I don't intend to find out. So I just jumpstart this little lad with tweezers. It's funny, when you're in the thick of theory and design, everything seems so clean and perfect, and by the time you actually get to building stuff, all that spherical cow idealism flies out the window, and you have all this bodge and jank just to get anything to work. So does it work? Well, overcharge protection kicks in if you drop the battery voltage down to 2.8, and with 5 volts of USB power connected, I can see the charge circuit measures about 4 volts. This should be 4.2, and I think what's happening is the charge AC is stuck in a loop thinking that the battery is full and thinking that the battery needs charging, so the MOSFETs rapidly open and close thousands of times a second, giving a slightly lower average voltage. But I'm not too sure about that. I guess we'll confirm this when we try charge a battery. Either way, this seems safe enough for now. Confident that the protections are working as planned, I soldered on the battery connector and stuck in the battery. And to my immense relief, the microcontroller booted up flawlessly, powered solely by the battery. I also tested USB charging, and as you can see by the little charge LED, it handles that perfectly fine too. Charge current is set to a max of about 400 milliamps, so for a 1600 milliamp hour battery, that's roughly 4 hours to go from dead to fully charged. Now, since I received my boards, all the testing thus far had been performed with an ESP32, not the NRF52. This is actually a hidden benefit of this design. Exclusively using the headers allows different kinds of Xiao boards to be used, which just wouldn't have been possible if I took the pogo pin approach because the location of the battery pads changes between models. However, somehow, I assumed that I could just swap in the nRF52 and program it in exactly the same way as the ESP32 using ESP Home, keeping dev time to a minimum and versatility as high as possible. But as it turns out, ESP Home actually doesn't support the nRF52. Or rather, it technically does, but it's very much a work in progress. For example, I couldn't get Deep Sleep or Bluetooth Low Energy to work, which for my ultra low power consumption plans are both pretty vital. In fact, they're so vital that I was pretty sure this entire project was dead in the water once I realized I couldn't use the nRF52. Now, you could still get things working with the nRF52 if you were willing to write the code in C yourself and not depend on something like ESP Home. But for me, that kind of kills the utility of something like this. If I have to write and test a bunch of code every time I want to use a new sensor, I'm just not going to bother, no matter how good the battery life is. So because Wi-Fi is so slow and power hungry, and because the efficiency of the C6 just can't compete with an ultra-low power chip like the nRF52, I was feeling pretty sure this project would fall well short of its battery life goals. Things at this point were looking a bit bleak. After some more dead plant staring and some reading of the ESP Home docs, which I definitely should have done in the first place, I realized a few things. First, development of the nRF52 is very active right now. In the docs and on GitHub, I can see there's a lot of ongoing work for the board and even the beginnings of support for Zigbee and Thread, all of which would be absolutely amazing to see. By the time you're watching this, support for this and more may already be added, so be sure to check out the docs or the repo. Also, shout out to this developer who seems to be making an immense amount of contributions for the nRF52 and ESP Home. My guy, if you're interested in any one of these prototypes, I'd be only too happy to send one to you as thanks. Just reach out and I can send it your way. So that's all really great and I super cannot wait to try out these features, but currently it's still out of reach for me as of making this video. However, the second thing I realized is the ESP32C6 is actually also capable of deep sleep. In deep sleep, I measured just 22.5 microamps for the whole board and the microcontroller. And while it's not as impressive as the records of the nRF52, it's still very impressive. Furthermore, I realized that a huge part of what makes Wi-Fi so power hungry is just how long it takes. By giving the board a static IP address, we can significantly reduce the time it takes to connect to Wi-Fi. And we can gain some more savings by enabling the fast Wi-Fi setting in our YAML. Testing with all these optimizations and learnings, using an ESP32 with Wi-Fi, here's the new power calculations. An active period completes within 3 seconds, in which time the board wakes, reads the temperature and humidity sensor, transmits over Wi-Fi, and returns to sleep. During this active period, my power supply readings hop around a lot. They're mostly under 100 milliamps, but I know that there's some transient spikes in there. So I'll estimate that it's about 100 milliamps average for the 3 seconds. Then in deep sleep, the board consumes 22.5 microamps for the remaining time, to a total of an hour. So every hour, the board consumes about 0.1 microamps. That means for our 1600 milliamp hour battery, we have a lifetime of 667 days or 1.7 years. 1.7 years on Wi-Fi. Even if we assume capacity loss from the cell just sitting there, we still get about a year and a half. Now listen, I'm as forgetful as all hell, but I think even I can remember to charge this thing at least once every year and a half. And the best part is, with better software, this number can only go up. As soon as the latest nRF52 features are added to ESP Home, I'll be sure to test if we can push this battery life even further. I think if we could get a low power protocol like Thread or Zigbee working, plus the insane efficiency of the nRF52's deep sleep, we could be looking at a battery life pushing up against the shelf life of these cells, something like 4 to 5 years on a single charge. At which point you just charge it using the USB cable and you're good for the rest of the decade. I definitely wouldn't call this problem solved. That's why the title of this video is in the present tense, but I think it's a pretty decent start. I'm going to run this in a few different configurations with different sensors and that, and after some real world usage, we can see how the battery life holds up to our spherical cow 18-month prediction. If you'd like to support the channel, you can check out my Patreon. Otherwise, thanks for checking out my stuff, and I'll catch you in the next one.